Welcome students, I am Srinivasan, Assistant Professor, Department of Computer Science. In this video, we will see process management. Here we are going to see what is the process, attributes of process, process control block, process life cycle, type of schedulers and context switching between processes, and between these topics I have added questions related to those topics from ISRO, UGC net and GATE CS question. So, it will give you more confident during the examination. So, here we will start with the basic definition. In simple words, a process is a program in execution. The execution of a process must progress in a sequential fashion. When we write a program in C or C++ and compile it, the compiler creates binary code. The original code and binary code are both programs. When we actually run the binary code, it becomes a process. So, a program, a source code is represented in binary format as a binary code, and that binary code is going to load it into the memory. Then the CPU is going to read the instruction, then it start execution. So, a process is a program in execution. A process is an active entity and a program is an passive entity. A single program can create many processes when run multiple times. For example, when we open a executable or binary file multiple times, multiple instances will begin. Just like when you click on Google Chrome multiple times, it will open multiple copy of Google Chrome. So, this is the first question from ISRO CS 2009. So, a process is a program in high level language kept on disk. B, contents of main memory. C, a program in execution. D, a job in secondary memory. So, just now we have seen answer for this question is a program in execution, option C. So, let us get into more details here. So, how a memory sees a process, how memory sees the process. When a program is loaded into the memory and it becomes a process, it can be divided into 4 sections: a stack, a heap, a text and a data. Here a process is divided into multiple parts. The first one is the program code, which is also called a text section, the source code that we are written, and the current activity including program counter, processor, register. Program counter, which is a register which holds next instruction to be executed, and the processor register which hold informations and computation results of the process, and a stack containing temporary data, which a stack stores just like a function call, which stores information and it can be retrieved later. Function parameters, return addresses and local variables, those are stored in stack. Function parameters, return addresses, local variables are stored in stack, and data section containing global variables, and a heap containing memory dynamically allocated during runtime. We know that it is a dynamic allocation. Memory is allocated dynamically when we run the programs. So, it is actually a heap, which is a dynamic memory allocation. So, these are the part of a process. So, attributes or characteristics of a process. So, each process must have these attributes like process ID, which is a unique identifier assigned by the operating system. So, you can see here each process have an ID. See the processes, each process hold a process ID like this: 68444 for Windows Explorer, OBS Studio that I am using to record this 4604. So, each process is have a process ID, and the process state We have many states, and we use only 5 states, and here it can be running, ready, wait, suspended, blocked. So each process must have a state like this. You can see each process have a state. You can see it's a running process is running. This process is suspended, something like, see this one, you can see such application is suspended, shell experiencing host is suspended. So you can see a process must have a state. And CPU registers, like the program counter, CPU registers must be saved and restored when a process is swapped in and out of CPU, which is a context switching. So CPU registers stores the information about the processes. And input output information, for example, devices allocated to the processors, open files, and etc. And CPU scheduling information, for example, priority. We have many algorithms for CPU scheduling. Here we have priority, whether it's a foreground process, whether it's a background process. So each process have a priority. So these are the characteristics of a process. Each process must have these characteristics. And process control block. A process control block is actually a data structure. All of the above these attributes of a process are also known as the context of the process. Every process has its own process control block. That is, each process will have a unique process control block. All of the above attributes are part of the process control block here. So each process have a process control block, and it stores information regarding the process. The architecture of a process control block is completely dependent on operating system and may contain different information in different operating systems. Here this is a simplified diagram of a process control block. The process control block is maintained for a process throughout its lifetime and is deleted once the process terminates. You can see the attributes of a process here. Process ID, for example, for a process it has to have ID and the state, whether it's running, it is suspended, whether it is terminated, and a pointer, priority, program counter, CPU registers, information, input output information, accounting information, and more details about each process. So when a process started, the process control block created, and attributes of the processes are stored in that process control block. Then we have process life cycle. When a process executes, it passes through different states. These stages may differ in different operating systems, and the names of these states are also not standardized. In general, a process can have one of the following 5 states at a time. So we have 5 states here. These are not standardized, and we have suspended, ready, and many type of states available. So we are going to generalize this in 5 states: start, ready, running, terminated, and wait. These are the 5 states we are going to see. So first state here, new or start. Newly created process or process being created. Okay, this is the first state. When a process is created, it is, the process state is start or new. And ready state. So process is created and then it moves to ready state. That is, the process is ready for execution. It is not running, the process is ready. And then run. From ready state, it can move to run state. The currently running process in the CPU, which is a running state. When a process is running, it is executing in the CPU. Only one process at a time can be under execution in a single processor. And wait or block state. When a process requests input output access, or it is suspended, or it is moved to waiting queue, or it is when there is a other process which have higher priority comes, then the lower priority process must be swapped out. In those situations, the process is put in the wait queue or in the wait state. And then complete or terminated, which is the process completes its execution. So, this is the process life cycle. So, we have 5 states: start, ready, running, terminated and wait state. No process, you can see the process here: start, ready, running and then terminated. It can start and it is put in the ready state, and then the CPU is given to the process and it start executing, and then it completes its execution, then leaves the CPU. And also from the start state it can go to ready state and it go to running state. If any input output request or during swap, if there any context switching, then it becomes then it will move to the wait state, from the running state to the wait state. You can see from the wait state no process cannot go to directly to running state. No process is directly cannot go to running state. It have to go to ready state and then only it becomes the it can go to running state. Okay, this is how the process life cycle actually works. So, the second question here: which is the correct definition of a valid process transition in an operating system? You can pause the video if you want to find out. The option A, which is wake up, ready, running; option B, dispatch, ready, running; C, block, ready, running; D, timer run out, ready, running. The correct sequence here is dispatch, ready, running, which is the correct sequence. This question was asked in ISRO CS 2009. And third question: a task in a blocked state. Here we can see a task or a process. A task or a process. A task in a blocked state, option A is executable, B is running, C must still be placed in the run queues, D is waiting for some temporarily unavailable resources. As we already seen, in a blocked state, block or wait, blocked state or a wait state is waiting for some temporarily unavailable resources. That is the correct answer. Waiting or blocked state is when a process has requested some input or output and is waiting for the resources. So, option D is the correct answer. And then CPU bound versus input output bound processes. A CPU bound process requires more CPU time or spends more time in the running state, which is a process needs more CPU time, less input, less interaction with the input output devices, and an input output bound process requires more input output time and less CPU time. An input output bound process spends more time in the waiting state because it interacts with the input output devices. So, when there is an input output device, when there is a requirement for input output devices, then the process is moved to the waiting state. So, this is a CPU bound process and input output processor. So, here the scheduler, we will see long term scheduler next. So, the long term scheduler must select the combination, must select the mixture of CPU bound process and input output bound process. For example, if we select only CPU bound processes, then input output devices will not be utilized efficiently. If we select input output bound processes, then CPU is not going to be utilized efficiently. So, long term scheduler must select a mixture of both CPU bound process and input output processes. Here we have type of schedulers. There are 3 type of schedulers: long term scheduler, short term scheduler and medium term scheduler. Long term scheduler makes a decision about how many processes should be made to stay in the ready state. So, this decides the degree of multiprogramming. So, what is multiprogramming? Number of processes in the memory is known as multiprogramming. So, degree of multiprogramming is number of processes in the memory. If I say 5 processes in the memory, then it is the degree of multiprogramming is 5. So, once a decision is taken, it lasts for a long time, hence called long term scheduler. So, I already told you about CPU bound input output bound processes. So, the long term scheduler must select a mixture of both input output and CPU bound processes. And short term scheduler, also known as dispatcher. Short term scheduler will decide which process to be executed next, and then it will call dispatcher. A dispatcher is a software that moves processes from ready to run and vice versa, to run to ready. In other words, it is context switching. Medium term scheduler, suspension decision is taken by medium term scheduler. Medium term scheduler is used for swapping, that is moving the process from main memory to secondary memory and vice versa. So, these are the type of schedulers in process management. Here long term scheduler which selects processes which are created. When we create a process, then the long term scheduler selects a mixture of both input output and output bound processes, and it put into the long term scheduler. And then short term scheduler which select processes that are loaded by long term scheduler. So, here short term scheduler or dispatcher select processes which are loaded by the long term scheduler. And here a dispatcher is a software that moves processes from the ready state to the run state and vice versa. And the medium term scheduler is performing the swapping here, that is from the CPU, from the main memory to the secondary memory, and also from secondary memory to the main memory. So, these are the type of schedulers available. And the comparison among schedulers here is long term scheduler, short term scheduler and medium term scheduler. In terms of calling, long term scheduler is called as a job scheduler, short term scheduler is called as a CPU scheduler, and the medium term scheduler is called as process swapping scheduler. Long term scheduler is lesser than, its speed is lesser than the short term scheduler, and short term scheduler is faster among long term scheduler and medium term scheduler, and medium term scheduler is in between both long term scheduler and short term scheduler. And long term scheduler controls the degree of multiprogramming, and short term scheduler provides lesser control over degree of multiprogramming. And here medium term scheduler reduces the degree of multiprogramming. Here I already told you about it is moving processes from main memory to secondary memory. So, it reduces the degree of multiprogramming, it performs swapping. And long term scheduler is almost absent or minimal in time sharing systems, because each process in time sharing system, each process have some amount of CPU. So, there is no need for long term scheduler in time sharing system. And short term scheduler is also minimal in time sharing systems, and medium term scheduler is part of the time sharing system, because in time sharing system we have to give each process a predefined amount of time. So, when the time ends, it must be swapped. So, it is a part of the time sharing system. And the long term scheduler selects processes from the pool and loads them into memory for execution. The short term scheduler selects those processes which are ready to execute. Here short term scheduler selects those processes which are selected by long term scheduler, and medium term scheduler can reintroduce the process into memory and execution can be continued. So, this is a comparison among schedulers. And the fourth question here, a virtual memory based memory management algorithm partially swaps out a process. This is an example of option A, short term scheduling, B, long term scheduling, C, medium term scheduling, D, mutual exclusion. So, here swap. So, we perform swap. So, it is actually the answer here is medium term scheduling. Whenever there is a swap, then it is a medium term scheduling. And then context switching. The process of saving the context of one process and loading the context of another process is known as context switching. Here context means process control block. Okay, the attributes of processes, process ID, state, the information, input output information, and the stack. So here see each process hold the process control block. So when we swap the processes from the main memory and load another process from the secondary memory to the primary memory, it is known as context switching. In simple terms, it is like loading and unloading the process from the running state to the ready state. When does context switching happen? When a higher priority process comes to a ready state. Here it may be a process is running and a higher priority process like interrupt, like a system process which have a higher priority runs becomes, and then we have to swap the running process to the ready state and giving the CPU to the higher priority process, and then an interrupt occurs. If an interrupt occurs and user and kernel mode switch, it is not necessary though. And preemptive CPU scheduling, if context switching happen, if preemptive CPU scheduling used, like shortest remaining time first, those preemptive CPU scheduling algorithms if used. So the here this is where the context switching is happen. Context switches are computationally intensive, since register and memory state must be saved and restored. To avoid the amount of context switching time, some hardware systems employ 2 or more sets of processor registers. When the process is switched, the following information is stored for later use. Here, program counter needs to be stored, scheduling information, base and limit register values, currently used register, changed state, input output information, and accounting information. So these information must be stored. So when we swap in the process again in main memory, then these informations needed to resume the process. Last question here: which of the following need not necessarily be saved on a context switch between processes? Just now we have seen this question was asked in GATE CS 2000. Option A, general purpose registers; B, transaction look aside buffer; C, program counter; and then D, option D, all of the above. Just now we have seen general purpose registers, okay, general purpose registers and program counter, both of them are needed. And here transaction look aside buffer, which is a cache, which is not needed because cache is invalidated after each time when we swap out a process. So the answer here is transaction look aside buffer. It is a CPU cache that memory management hardware uses to improve virtual address translation speed. So it is not needed when we it is not needed to be saved when we perform context switching. And fork, another question, which is a fork. Fork is a system call used in Unix. So fork is a option A, the creation of a new job; B, the dispatching of a task; C, increasing the priority of the task; D, the creation of new process. Yeah. So the answer for this question is the creation of a new process. Fork is a system call which creates a new process by duplicating the calling process. The new process, referred to as a child, is an exact duplicate of the calling process, referred to as parent. So these are the important topics in process management. So if you have any questions, ask in the comment section and I will be replying to you. Okay, that's it for in this video. We will see in the next video. Thank you all.